So remember, part 2, we're going to talk about notions and mechanisms around payment, reimbursement, and business models. I think a very important thing. So I don't want you to feel like we're diving past that. But let me go on in and just dive into a little bit of the technologies that are out there. And again, we'll highlight something on the Clarus a little bit tonight. We'll talk about Sita and one of the new algorithms that's with the new HFA. We'll speak a little bit on OCT angiography, which we've been working with in my clinic for a little bit over a year now, and full-blown kind of, we blasted the market with it, and then last talking about tying it up with Forum. So here's your image of a Clarus ultra-wide field, and I'll draw your attention to a few things that are on here. There's a small circle that's right in the middle here. That small circle is your direct ophthalmoscope. Now remember, none of this is to scale because magnification varies with some of these lenses, but it's just showing you the geographic area that's covered inside the retina. The second image that's right here, that rectangle, is your 90D. So not a 70, but a 90 diopter lens, just showing you what you can get if you're pretty good with it. Obviously less magnification there. The third circle going out here, that's your 20 diopter lens, using that with your binocular indirect ophthalmoscope. The next ring that we've got going out here is your 45-degree traditional fundus camera. And then the very last ring that's going around, and you'll see it in two pieces there, is the ultra-wide field image, which is taken, and I want to just get right out there. I think the steps, people start to think, well, is it one image? Is it two images? What is it? It's two images. It's got a pretty bright flash that's associated with it. But when the staff use it, and they understand how to use it well, which takes about 10 patients or 20 eyes, it's like operating a slit lamp, and they're very quick on acquisition. We've been using it in a clinical trial basis for what are called FDA validation studies in the US. We've been using it on a clinical trial basis with all of our staff. And when I had to give the first prototype back, not only my staff, but my docs were really pretty upset as we finished that study and got ready for the next. So it was really interesting to see their feedback. And we asked patients a critical question because we noticed the flash was bright right away. And the critical question that we asked our patients was, would you have the test done again? Once it was demonstrated to them what it was, and they had the imaging device, they had the image run and all of that. And every single patient that went through the study said yes. There wasn't one that said, nah, that flash was too bright, or this was uncomfortable, or that was uncomfortable. So I think that was a key part for us, and we ran it across 3 different technicians running the images, as well as our doctor review. So we had some degree of variability. Obviously, our N wasn't all that big since it was a narrowly defined study, but it was big enough for me to say, okay, there's something here for us to consider. Now, the other piece with this is those images that you see, those are auto-montaged. Those images are not taken and then hopefully you can glue them together and you grab this vessel and that vessel and yeah, boom, there it is. They're auto-montaged. The algorithm that's written actually does that. And the field that you're looking at here is a 200-degree field. You can actually take up to 6 images. So you've got a little bit better specs on that. And this was taken, these images can be taken on a 2.5 millimeter pupil or larger. Smaller than 2.5, you get too much artifact with it. So keep a couple of those things in mind as you're taking the image. We found, and we had a dedicated room that was probably about that big right here, where we have our field in one corner and we have our Clarus in the other. And we took our images in that room where we can control the lighting. We found that wasn't a critical issue. On a 2.5 millimeter pupil, we did see with these patients that it seemed to take about 3.5 plus minutes on acquisition. Whereas if we had a pupil that was at 3 millimeters, it took us 2 minutes or less in terms of total acquisition time for the staff from eye to eye to eye. And I'll show you a little bit about how that gets taken, but you can see, and just as I scroll back and forth between these two pieces, you can see this is the same image as what's right here. And you don't lose anything in resolution when it comes to the image that's on the screen here. And I could blow this up one more time, and I have a couple examples of that we'll look at next. I think that that's really a critical piece about this, is this is as good as any fundus photography. And we'll talk a little bit about the color and those comparisons, but even at that, it's a true color. So it's got a couple of benefits in terms of being able to use the Clarus. You can actually use the Clarus in a few different modes. One is in true color, which you see up at the top, and that's represented by the large image that's in front of you. The second is a FAF green, a FAF blue, an infrared. You also have filters on the true color. So you can do a blue filter, you can do a green filter, you can do a red filter, and I've got a couple of examples of those. That's important because it operates just like a traditional retinal camera. The next piece here is this infrared piece that's down below. The infrared camera is used right now to sight the retina and kind of center on the retina. But what we found that was a lot of fun, and we started toying with, because we tend to go off of on our own beaten path in the clinic, is we started playing with meibography on it. So we started flipping eyelids inside out and getting a white gland image. So you can't do it with an infrared source that's coming from underneath like you do with a LipiView or a LipiScan. But you can get a white meibography image using the infrared light source that's on there. And it would be really cool if that kind of came out in a little bit more of a module, because you can take that and plug it in with the external eye function, and that's where we combined those two together and said, let's see if we can make this footprint a little bit more useful for us. The next piece about the technology that you should understand is that the technology is a spectrum. The technology is not as that image to the far left or your right shows, where it's got a blue, a green, and a red. It's actually the spectrum that's listed down in this piece. So sorry for the busy slide, but it really shows us what the difference is in terms of the scan. And it's without this spectrum, you don't actually get the true color. That's what gives you true color, because it's taking the entire spectrum and it's combining that as the algorithm works. So this is just your OCT. This is your setup on your Clarus. That's the chin rest, single chin rest. The camera is kind of like got a little, I don't know if you call it a geolocator or what, but as it pivots around the patient, it knows where it is in respect to the midline, so it knows if it's right eye or left. Your staff don't have to label it. So you can't get a misaligned, oh, you wanted the right eye. Yes, that would have been nice. We've all had that in clinic. Go back in there, get me another one. I can't relabel this one. So that's useful about it. You can see the little swivel that's around it. And then I'll highlight just two things on this piece right here. And so if you look here and you look here, there are two drivers that are centered on the pupil. My staff actually found that when they started to take images on the Clarus, they never had to look right in here at the retina until the very end. The only time they looked at the retina at the very end was to get a fine focus. But what they did to draw the image in was they paid attention to what was happening in the centration on the pupil, and aligning those two pieces got it right into where they needed to take the correct image. And then when the fixation target switched, they switched that over. Now, with the Clarus, you do have some of the challenge with the eyelash on a more narrow eyelid or a more inset eye. So you just got to be cognizant of that. Again, after about 20 eyes, 10 patients for each of our staff, they got used to where that was and they saw it right away. And we're able to just tell the patient, just pull their eyelid down just a little bit. So from a comfort standpoint, now they don't have to jam their face in there, and maybe there's just a little bit of a pull down that's happening on that lower eyelid. So red channel separation, as I was sharing just a moment ago, there's red, green, and blue separation. I like devices that connect us to a next set of utilities or devices, or that seem to have overlapping functions, because they can lead me to other management conditions. So I'm going to draw a couple of correlations to what I think relates to an OCT here in just a moment. With the red, you're all familiar with red and with green. So red free photography and what these things tell us in our differential diagnosis. No different, that's very useful. But this piece right here I wanted to highlight for you, because the blue on this, I like the blue a lot better than what I've seen on some of the traditional cameras, and just because of what you get with the RNFL. And if you don't have an OCT and you want to know what's happening with an epiretinal membrane, the blue can be a really useful channel there as well. Now, if you have something like Forum, where you can take in glaucoma workplace, you can take an image of your nerve, and you can take your visual field. You could actually put this blue on there and look at RNFL changes on that photo adjacent to where the visual field changes, and corroborate or correlate data and information around a diagnosis of glaucoma. So this can be another useful piece in that regard. So true color, and the reason I bring this image up is, again, back to just looking at it at scale. You can see how big that one is, and I could have got much larger. But what I'll point out to you here are these fine little drusen deposits, just in a differential. So we're looking at this, well, what is it, right? You're going to throw up different filters potentially on this. But in particular, when you've got it at scale and you've got no distortion, you actually see what's happening in the anatomy in this particular set of images. In terms of true color when it comes to a nerve, this is a really important distinction. Credit to Zeiss, other ultra-wide field. That's an Optos. They don't necessarily, in certain places, have this labeled as such, but there's only one other really ultra-wide field out there. So when I'm talking about that, you should know that I'm talking about comparing this to what my experience has been with an Optos. Okay? When we look at the different images as we go across, you see a white light image. Which is, there's other technologies that are out there with white light images. They're really not very much used. The ultra-wide field technologies are using a scanning laser ophthalmoscope, and so that's a little bit different in the way that you get the acquisition. And then you've got a true color image, so you've still got that pink kind of image to the retina, or to the edge of the optic nerve, and then your red or browns around the retina. And I'll show you a few a little bit later that compare like 6 different images of a disc. And you can see how that true color is maintained through the disc, so you can get a real diagnosis as you go through it. The other piece with the Clarus that I like a lot is when we're in the image here. So you've got the posterior pole, right? Which traditionally with an image, you might get this and you might get it blown up. But somebody getting an image out here on the periphery, you kind of lose some of it gets grainy, it gets out of focus. It's just not really clear all the way out to the posterior pole. There's your disc with your posterior pole complete, and there you are all the way out to the edge. And you can see in all 3 of those images, there's consistency in the clarity of the image. That's the same image that you were looking at just beneath it. So right here, just blown up into pieces. And again, I could have taken that and I could have made it even larger on the screen for you. But it just shows you the consistency of the image. And while these are slides that we've got prepared for this particular presentation, I can't show you the slides from the study patients that we had right now, but I can tell you that the slides are identical if I were to pull these up from the patients that we have experienced. And that has to do with the way the FDA does trials. So just to share with you, that's been my experience exactly. AMD patient, when you look at this particular case and you're looking there, you know something's going on, but what is it? I blew it up just a little bit. If you were up here closer, sorry for those of you in the back, you can see all the drusen that's scattered here on the macula. I should have actually blown that up to the full screen, but again, the same kind of elements that we're discussing before, and all the way out to the edge. So you're out into the periphery, you still maintain the same clarity all the way up into the edge. And then one more example, a little bit darker of a fundus that we've got here. So we've got this especially in a lot of pockets within the US. This one, you've got an AV malformation that's in it there in the center, but you can also go all the way out to the edge and still have the same sort of demonstrated clarity as we get to the edge or to the periphery. And this last one is just a hemorrhagic PED that we're looking at. Still the same size and largeness. This last one that I'll put in before I dive into a couple of the other slides around true color is I want you to note the edge of the image comes right here and comes right here. And this image is going diagonal. And what's unique about this is not the pathology, but it's the angle at which the images were taken and the fact that, again, these were auto-montaged. So instead of going sideways, we knew that the pathology was sitting, at this like 11 o'clock or 10 o'clock sort of angle, and we took those 2 images, and then it auto-montaged those for us as well. Still the same clarity there, clarity all the way out to the edge. So glaucoma. What if we were to use this in glaucoma? Now I showed you blue, and I showed you a blue filter in it, but you need to still be able to take what in glaucoma? What kind of photos of the optic disc? Stereo pairs, right? So here's your stereo pairs coming out of that. And you'll have to take my word for this because I did it on the airplane and almost made myself sick, is if you cross your eyes just a little bit and you take a look at those, you can make depth pop out of these 2 images in terms of the way in which they've been snapped. So there's a stereo pair function that's on here as well. True color. Remember I said there are a couple of photos of a few discs, and what I want to draw your attention to is not the color of the fundus. I want you to draw your attention to the pink, the pink, the pink, the pink. Give me a little pink on that one. And the pink that's right in here on these glaucoma. Really consistent optic nerve images all the way through, not depending on the fundus. And the other key component of that is you didn't play with the intensity of the light source. I can't stress that enough. Because how many of you have had somebody sit down on a traditional camera, I don't care what it is, if it's a VisiCam, if it's a Topcon, if it's a whoever's camera, right? And they've got to be really good at taking the photos. There's less of that in this particular unit and device from a utilization standpoint.